Hello and welcome to University Physics. So we are solving quantum physics by HC Verma and we are in chapter 3. So let's move to question number 13. And question number 13 is which of the following represent a realistic wave function of a particle? So basically we are given four functions and we have to check whether these functions are realistic wave functions or not. So condition of realistic wave functions are properties of realistic wave functions are it should be finite everywhere. It should be finite everywhere. It should be continuous. It should be continuous. Everywhere. And it should be square integrable. And it should be square integrable. Finite everywhere. This condition leads to the probability of finding the particle. Probability of finding the particle is finite. And this square integration leads to condition of normalization. So if any wave function is not square integrable, we cannot normalize it. And if we cannot normalize it, we cannot find the probability of finding the particle at any point. So now let's check the first function. So the first function is psi x is equals to a e to the power x square by a square and exponential ikx. So let's first change the first condition. Let's check the first condition, that is it is finite or not. So at x equals to 0, the value of wave function psi x is equals to a. Exponential, if we put like this, e to the power 0 and e to the power 0, so basically it comes out to be a. Now let's check the value of the function at x tending to infinity. So psi x on limit x tends to infinity, it will take the value e to the power, here we'll put infinity square, infinity by a, it's a square, and e to the power ik infinity. So basically ik infinity, this is sinusoidal. Its maximum value will be 1 and its minimum value will be 0. Now let's check this portion. So this leads to a e to the power infinity, means infinity square is infinity, and e to the power ik infinity. So this leads to value infinity, that is undefined. So the wave function psi x a e to the power x square by a square and e to the power ikx, it diverges as x tending to infinity, means its value is not finite. So this is not a realistic wave function, not a realistic wave function. So now let's move to part B of this question, and part B is psi x a e to the power minus mod x divided by a and exponential ikx. So we can also break this function in two parts, like psi x is equal to a e to the power minus x by a e to the power ikx. This is for x greater than 0 or 0 to x infinity, and a e to the power x by a e to the power ikx. This is for x less than 0 or minus infinity to 0. So we have to check all the conditions, that is continuity, its continuity, whether it is finite or not, or whether it is square integrable or not. So, and this part e to the power ikx, this is called the propagator part of the wave function. Propagator, and we can also write e to the power ikx as cos x plus I sin x. So whether we put 1 to infinity any number in the argument of cos and sin, it will give a maximum value of 1 and minimum value of minus 1. So if we take the mod of this, so its value is nearly equals to 1, its maximum value 1 and minimum value is minus 1, so it will be always finite. So it will be always finite. So we have to check the rest part of the function, that is this one, these parts. So now let's check it. So at x equals to 0, the value of psi x will be a. It will always be a. And for x tending to infinity, so x tending to infinity, so we have to take the first part of the wave function, that is this one, since that the function defined for the positive reason. So let's check the value of function when x tending to infinity, a e to the power minus infinity by a and e to the power ikx, the propagator part, which gives the value nearly equals to 1, or when we put e to the power ik infinity, it will give the maximum value 1. We'll check the maximum value to be 1. And this will be equals to a e to the power minus infinity times e to the power ikx, so it nearly comes up to a 0. And for x tending to minus infinity, so we have to take the second part of the wave function, that is psi x tending to minus infinity, a e to the power minus infinity by a. We will put x equals to minus infinity in this part, and e to the power ik minus ik infinity. So again this will be 0. So basically all these three, the value of x equals to 0, the value at x equals to 0, the value at x tending to 0, and the value at x tending to minus infinity are finite. Now let's check its continuity, whether the function is continuous or not. So our wave function psi x is equal to a e to the power minus mod x by a e to the power ik x. So Now let's check its continuity. So limit h tending to 0 psi x plus h, this will be a e to the power minus mod x plus h and e to the power I k x plus h. So we can also write it as a e to the power minus mod x e to the power minus h e to the power ikx and e to the power ikh, and all these at h tending to 0, limit h tending to 0. So we will get a e to the power minus mod x by a and by a and by a e to the power ikx and e to the power minus mod h by a and e to the power ikh, and limit h tending to 0. So this part is nothing but psi x and limit h tending to 0 e to the power minus, let's put the value 0 by a and e to the power ik into 0. So exponential 0 is 1, so this is equals to psi of x. Obviously this one, limit h tending to 0. So and similarly we can prove limit h tending to 0 psi x minus h is equals to psi x. So the function is continuous in either side of its value psi x. It's the value of the wave function psi x is continuous. So now let's check whether it is square integrable or not. So our function wave function is psi x is equals to a e to the power minus mod x by a e to the power ikx, or we can write also this as a to the power minus x by a e to the power ikx for x greater than 0 and a to the power x by a e to the power ikx for x less than 0, and its conjugate will be psi star x will be a star e to the power minus x by e to the power minus ikx, and psi star will be a star e to the power x by a e to the power minus ikx. So let's check its square integrable condition. So psi star psi dx, and we will take the limit from minus infinity to infinity. So we get mod of a square e to the power minus plus 2x by a and e to the power ikx e to the power minus ik as this is from minus infinity to 0 dx plus from 0 to infinity e to the power minus 2x by a to the power ikx and e to the power minus ikx times dx. So this exponential factor, let's cancel out, and we are left with mod a squared integration minus infinity to 0 e to the power minus 2x by a times dx plus 0 to infinity e to the power this plus minus 2x by a times dx. So yeah, its value will be mod of a square, and the value of this integration will be a by 2 constant times 2x by a limit minus infinity to 0 and plus minus a by 2 and e to the power minus 2x by a 0 to infinity. So mod a squared a by 2, when we put 0, so this will be 1 and minus 0 and again plus minus a by 2 and when this so 0 minus 1 and this is so a by 2 plus so a times mod a square. So yeah, this is also finite, so it is square integrable. So since it satisfies all the conditions, so this is a valid wave function. So psi x is equals to a e to the power minus mod x by a e to the power ikx is a valid wave function. So now let's move to the third part of this question. So the wave function is given as a sine kx by x square. So let's check whether it is finite or not. So at x equals to 0, the wave function psi x a sine kx by x square, this diverges. So we can also look this as a sine kx by kx and 1 by x, k by x. We have multiplied the numerator and denominator by x, and now let's take the limit when x tending to 0. So a limit x tending to 0 sine kx by kx and limit x tending to 0 k by x. So basically this term will give us 1 a times 1, but the term k by x diverges. This goes like 1 by infinity. So the final result that the function diverges and it gives the value infinity. So basically this is not finite. The function psi x is not finite. It doesn't have a finite value at x equals to 0. So it is not a valid wave function. Not a valid wave function. Valid wave function.